Now let's get started. The next presentation will be the performance evaluation model to enhance lifecycle productivity in modular and offset construction, a process-oriented approach. So the presenter will be Babak. So the floor is yours.
Thank you. Hello, everyone. Thank you for joining. I'm PhD candidate studying in Concordia under the supervisions of Dr. Han and Dr. Nasiri. So over the past 2 decades, the global construction productivity has remained stagnant, increasing by only 10% between 2000 and 2022. Despite rising demand for housing, the industry still faces affordability challenges in which the life cycle productivity will be critical to addressing these challenges. MOC offers potential solutions by moving to the controlled factory environment and adopting lean manufacturing principles. However, this method, the adoption remains limited, holding only 6% market share in 2022. Many stakeholders reported higher than expected costs compared to conventional methods, often failing to fully benefit from lean practices. Processes are still dominated by conventional construction methodologies. Its unique processes and parameters are still neglected, which results in unbalanced life cycle process flows, which is engaged with disruptions and waste. Also, current performance evaluation tools fail to effectively assess MOC process performance due to their poor tracking of concurrent activities, inadequate resource utilization assessment, inability to identify waste causes, and failure to address logistic challenges. These gaps impede precise process performance evaluation and hinder the industry's shift towards more efficient and lean-driven practices. To identify research gaps, conventional KPIs in general and lean and regular road transportation and on-site construction KPIs with respect to productivity and process flow were investigated. Also, productivity evaluation models in MOC with respect to the three components of project tracking and control, such as progress measurement, performance assessment, and forecasting were investigated. However, MOC studies relied on conventional construction KPIs, the process flows and sequencing unique to MOC, which are still not regarded. These studies focused mostly on manufacturing phase, not the life cycle. They did not effectively address the concurrent activities, or they were able to identify the root causes of inefficiency. The interaction among the processes and between life cycle processes are not regarded, and there's still lack of methodologies that compare actual performance with the benchmark, the predefined benchmark. So given the differences between off-site and on-site construction methods, modular construction should be treated as a process-oriented approach that supports repetitive operation and its distinct process flow, incorporate resource building to identify waste, and includes MOC-specific KPIs to assess lifecycle performance. In this respect, this research introduces a process-oriented approach to systematically evaluate lifecycle productivity using proposed MOC-specific KPIs. The objective is achieved by proposing KPIs tailored to various lifecycle phases to measure resources utilization in terms of workforce, creating a simulation model integrated with these KPIs to assess lifecycle productivity while considering resources allocation in terms of workforce and workspace. And finally, running intervention scenarios using the simulation model to analyze the effectiveness of the proposed KPIs in identifying root causes of waste and lifecycle process enhancements. To propose KPIs aligned with the lifecycle processes, process flow of one single module was mapped using the sequence diagram and insights from literature review, modular building industry reports and interviews with industry experts, such as Stack Modular and Small Modular Canada from Canada and ModLogic from US, Pennsylvania. The proposed KPIs attempt to identify various sources of waste with respect to resource utilization. For instance, within the manufacturing stage, the module defect modification attempts to measure the amount of time spent to repair defective modules across the production line. Before developing a simulation model, the lifecycle productivity equation is formulated, which is surface area of modules installed on site per total project spent or work hours. In this respect, system dynamic simulation model is used which is able to integrate management actions, performance evaluation, and process performance improvement involves management actions. Furthermore, system dynamic model can examine the effects of intervention scenarios on lifecycle processes. It is capable of modeling continuous processes and the cumulative effects, such as lifecycle productivity. And also, it can consider feedback loops and cause and effect relationships between lifecycle parameters. So this means how changes in one aspect of process can ripple throughout the entire life cycle. In this respect, causal loop diagram and static flow diagrams developed for all phases of the modular construction. The simulation model was calibrated with a residential modular project located in Kenora, Ontario, provided by Smart Modular Canada. Also, the simulation model was validated against the real values. Furthermore, the objective of the intervention analysis is examining the behavior of KPIs under each scenario. Each intervention was devised within the aim of improving lifecycle process performance. This involves several key steps: identify interventions and their boundaries, run each scenario using a developed and validated system dynamic model, and also perform statistical tests and modeling techniques to assess which KPIs efficiently identify root causes of waste and contribute to lifecycle process improvement. So, in this respect, the normality tests were performed, such as histograms, quantile plots, kurtosis, skewness, and Shapiro tests on each proposed KPIs were applied. The quantile plots and histograms revealed that the data set for each KPI deviated from the normality. The skewness and kurtosis values exceeded the acceptable threshold for most KPIs, thereby violating the normality of the assumptions. Also, the Shapiro test yielded p-values below the significant level of 0.05, leading to the rejection of the null hypothesis. So, non-parametric statistical tests were employed. So these diagrams, the histograms, and the quantile plots you see is only for manufacturing. All these diagrams were developed for all the proposed KPIs for the entire life cycle. Further, to examine the strength and direction of the relationship among the proposed KPIs, Spearman's rank correlation coefficient was applied. Since all the coefficients fall within the acceptable range, the proposed KPIs are deemed suitable for inclusion in the developed model. In this respect, to identify those that significantly contribute to lifecycle productivity improvement, another round of quantile regression was applied. The analysis involves multiple iterative rounds during which the p-value for each KPI was computed. KPIs with p-values exceeding 0.05, signifying a lack of statistical significance, were systematically excluded from subsequent iterations. This process continued until all remaining KPIs demonstrated statistical significance. As this is in round 5, analysis round 5, all the remaining KPIs remain significant. So, in conclusion, this approach helps the production managers to effectively identify root causes of process waste with respect to resource utilization and contribute to lifecycle process improvement using the following KPIs: workflow interruption and module defect modification KPIs within the manufacturing stage, stationary occupancy at factory module loading and module traveling time within the transportation stage, and shipment damage inspection and site fit reports within the on-site installation. Thank you.